Hey there everybody, Mr. Doolin here. We're going to talk about flux, specifically electric flux. What in the world does that mean? So flux is a way of measuring the number of field lines going through a particular area. So I am going to use a couple of different examples here to try and clarify what I mean by flux and specifically electric flux. But the first one I want to talk about is from this website falstad.com or falstad.com. I don't know how to pronounce it. But this person has made some very, very cool interactive three-dimensional vector and field demonstrations here, and I wanted to talk about use this weird mustard colored one here with the green field lines to talk about what's going on. The lines are the green field lines, which are the electric field at this particular location. They're going through that particular plane, and you can see here that the plane, if we consider that yx, which you can see up here, that's yx, then the field lines are only in the z direction. So this is what we would call an orthogonal vector. The thing that I want to clarify, though, is exactly how do we define the area of a surface when we're talking about field lines, and it's not obvious, or not, I guess, intuitive. Okay, so I would say that hyperphysics is a good place to start. The definition of flux, which is the capital letter phi, technically pronounced phi, but I'm not going to do that. It's the dot product of the E field and the area vector. The area vector is at a right angle to the surface, always. So you can see that here we've got this blue plane. This guy would be the area vector, this black line labeled capital A. And it's no matter what surface you're talking about, the area vector is always at a right angle to it. Well, flux is defined as how much of the area vector is parallel to the field lines, in this case electric field lines. Again, we're talking about the field lines at a particular point in space. And if I switch back to this, you can see the field lines are all parallel to each other. So whatever charge distribution must be causing this E field, or for whatever setup we're dealing with, the E field's constant in this particular chunk of space. So this 3D cube that's drawn here, and this particular region of space, the E field's constant. Okay, so the way we're going to deal with this is to think about how can we add up the relationship of the E field at this particular point in space, dot product with, I think that's a verb, dot product, dot producted, it's still not good enough, but it's E dot dA, and then integrate over in the entire surface we're curious about. So you can imagine up here in this example, here's one field line, here's another, here's another, here's another, and what this calculus definition gives us, by the way, this is one formulation of Gauss's law that we're going to learn very soon. What we're saying here is, okay, for the entire surface, if I can come up with a calculus way to describe the surface as a function of charge or surface as a function of E field, then I can do an integral that will tell me a quantifiable value for flux. More importantly, we're going to use it to figure out, which seems a little non-intuitive right now, but I swear it'll make some sense. We're actually going to use this idea to figure out the E field by using some pretty ridiculous symmetry to do our integral. So the integral of our dA will end up being very straightforward. But let's talk about a couple of other examples of what I mean. So this is here we've got some surface area. In fact, this is a infinite plane of charge, but it really demonstrates this field line thing pretty well. Let's switch to what would look like for 3 dimensions for a point charge. So we've got a single charged particle there, electron and proton. As a matter of fact, by default, the software makes it an electron. You can click this guy and reverse it. Not that it matters for our demo. Oh, and you can also make it rotate, which is cool looking. But, and you can see up here, the X, Y, and Z planes are labeled. So this bottom square down here, the one that's farthest away from me, would be the YZ plane, and the way I've got it sitting right now. And this line right here, that's the x-axis. So you can imagine what the field lines look like. Actually, we don't have to imagine it, we can see it. In fact, now we've got, for each side of the cube, we now have our own square. That's what that's called. where the field lines are going through it, and you can see that they're not at a right angle. So when we come back to Gauss's law, I'll remind you that really we want the field lines to be at a right angle to the surface at all points. That's one of the things that would be helpful to say. Or if you could describe the surface at any given radius away from your charge distribution or your surface that you're drawing. If you can say that the E field's constant along it, you could use that. Or if you can describe, well, that's good enough for now. That's a good way to think about it. So another good example of, or another weird kind of way to look at this, let's actually go to the conducting sphere and point charge. And I'm going to make the sphere a little bit bigger here. And I'm going to make the sphere potential, I can show you here, it's now they're similarly charged, oppositely charged, and you can see the interaction between the field lines in this example. Now there's a lot more we need to do other than just play with this three-dimensional gadget, but you can see that the field lines here, I want to drag the potential around. The way the software is doing it for the sphere, not so much the point charge, which is the same, but here we can actually see the sphere. Notice that the way we deal with this is the field lines are always at a right angle to the surface, okay? So when we're talking about flux, we're typically talking about, well, how many field lines are perpendicular to our particular surface. If we, here, let's pick a cylinder. Here's another really useful example. So imagine now I've got a solid cylinder that's conductive, and then you put it in an E field. So if there's an E field passing through space, and there's a cylinder that's capable of conducting charge, and I want you to see that it ends up here. Let's make the cylinder a little bit bigger. And you can see the field lines always end up at right angles. So whenever we're talking about flux through a surface, charged or non-charged, we're going to be dealing with the perpendicular component. Now if I rotate this a little bit, think about the ends of this sphere, which have area, whatever the radius is, pi r squared. So the area we're curious about here would now be the surface of the cylinder, not the outer edges. So when we're, and this isn't necessarily a super convenient way to think about it, but you always need to look at your particular scenario, be able to envision, okay, is the particular area I'm talking about at a right angle or not at a right angle? So because the parallel nature of the ends of this cylinder compared to the E field, that they don't have any effect on the overall electric system here. So when we're dealing with Gauss's law, we're only curious about where the E field and the area vector are at right angles to each other. I'm sorry, only where the E field and the area vector are parallel to each other. Here the area vector would be coming out of this thing, so that would be, I guess, in the z direction. Notice that the field lines only exist in these little slices that are in the xy plane. So relative to the z, there isn't any, okay? Now I recognize that some of this stuff is hard to do, and we're going to talk about it again and again and again, but let's go back to the point charge. Actually, let's look at the point charge and a conducting sphere. I'm sorry, point charge. There's so many of these cool gadgets, I get distracted. Which is fun. I mean, you know, playing is fun. That's fine. I don't have any issue with that. Here, let's just put a conducting the sphere back in the E field, and then let's make the radius something like that. And you can see here that there's some E field that already exists, and then we put a conducting sphere in it. Look at the weird interaction between the capacity for this thing to conduct electricity and the field lines. Then you can switch over here to oops, that's cool, but that's not what I want to see. I want to look at the a dielectric sphere, which means if you want, you can have it not conducting electricity at all. So now you can see there's a wire frame there, and the lines are just passing right through it. And the more conducting the thing is, the more it bends the field lines, as you can see. So there's obviously a lot to deal with here, but in this video, all I really wanted to get at is what in the heck I mean by flux. And flux is the relationship between the area vector, which is always perpendicular to the surface, and the E field lines. If those two things are parallel to each other, you actually have a pretty straightforward integral, or a pretty straightforward calculation. If they're not, then you got to treat it as a dot product, and you might have a little bit more work to do. And to finish up, the flux by itself isn't all that useful of an idea without combining it with either symmetry or Gauss's law, which will help us use the flux to figure out the E field or the charge enclosed. It's kind of like a stepping stone. So it also comes up in many, many other applications in astronomy and physics, in optics, for example. You can talk about energy distribution as a function of area. And so you can imagine that the math can get pretty complicated. Imagine a vector field, but instead of in 2D and 3D, and then trying to calculate for every given point in space the relationship between the field lines and the area. Well, that's what flux is useful for. All right, I hope at this point you do give a flux. That's right, I went there.